Thank you for that gracious introduction and for leaving your watch behind here. It's very, very helpful. Make sure I stay in time. And thanks to Dara Lombard as well for inviting me here. I'm delighted to be a speaker in this exciting program. And it's particularly good to have the opportunity to talk about a pretty simple, all-encompassing theme: the entire universe. That's what we're going to be talking about tonight, ladies and gentlemen. I want to begin with an observation that Einstein made in a letter to an old undergraduate friend of his 3 years before Einstein died. And it concerned what Einstein believed was the central miracle of science, physical science. And that is the fact that we find ourselves in a universe that has a deep underlying order. That order enables us to understand or forge an understanding of the universe and do so in a mathematical way. 150 years ago, the peerless thinker about the natural world, James Clerk Maxwell, gave a lecture on the relationship between mathematics and physics, broadly speaking, the same topic as I'm talking about tonight. Now, I can't, of course, promise to bring you anything like his depth of thought and experience, but I would just note that at the beginning of that lecture, he said that this relationship between the two subjects is far too magnificent for someone of his ability to discuss. So I hope you feel very sorry for me trying to do justice to this subject from my relatively low perch on things. But I will do my best and reflect on some of the best thinking I think that is going on this subject in this institute, which, as you'll hear, has played a central role in the story in the past few decades. Let me begin by just giving a quick flyover of the topics I will be talking about. You have to start somewhere, and a really good place to start on this topic is a person you may have heard of, Isaac Newton, and the torch of mathematics that he and others helped to shine on the natural world. Theories of gravity, electricity, magnetism, atomic forces are based on mathematics, and we'll be talking about the great successes that arose from that observation. But the path between physics and mathematics, the relationship with them, hasn't always run smoothly. And there was what has been rather graphically noted by Freeman Dyson, a divorce between the subjects directly after the World War II. But they did get back together. As you'll hear, Oxford has a lot to do with that. And I'm going to be talking about the roles of the two foundational theories of 20th century physics, quantum mechanics, and the basic theory of relativity as the basis, or the engine, so to speak, of that close relationship. And I shall be asking whether it really is true that mathematics is today, broadly speaking, leading physics astray, as several commentators have argued. And finally, just to embarrass myself and give you some amusement, I'm going to leave hostages to fortune by looking to the future of the subject. And as you know, all predictions about the future of science, like the future of British politics, are completely worthless, but it's entertaining nonetheless. All right, let's begin with the event that happened on an otherwise unremarkable summer's day in 1687, the 5th of July. Check the weather reports, quite an ordinary day, nothing particularly going on. It was a Saturday. And on that day, in London, a 3-volume book was published for the first time. And this was the book, the Mathematical Principles of Natural Philosophy. Now, this book is quite famous now. We call it Newton's Principia. It sold reasonably well. They actually tried. It was quite a difficult job to actually get to sell these books. But of course, now, as many of you will know, this has the status as the beginning of the mathematical approach to physical science. And it was written by Isaac Newton, Cambridge professor, who was, if I may use the word genius once, is the presiding genius of this subject. He was, by his own description, a natural philosopher. Remember, the word physicist did not, he would never have used that word about himself. He was a natural philosopher, a thinker about the natural world. The natural philosophy at that time was thought of as the rational study of God's creation. Very important that God is in there. As your Oxford historian Rob Iliff, in his classic book, Priest of Nature, has demonstrated, Newton regarded himself more than anything else as a man of God, to use a term that would have been he would have used. He was also a mathematician, very important. And just to underline his variety of skills, he was not just a great experimenter, he was a great thinker about the natural world and a mathematician. So he really was blessed with a terrific, we would now say, skill set. In that book, he set out what we now, pretty well all of us, even those who are not versed in this subject, know is the way you do mathematical science. At a very basic level, you have a basic mathematical structure, you make predictions about the natural world, and you check those predictions against the most accurate observations one has. If they disagree, then you feed back, you modify the theory, and then put it back to nature. You're trying to account for that order, so to speak, in the universe around us. And in this monumental book, not easy to read, let's be clear, this was not J.K. Rowling, right? This was a tough read. It was in there was the law of gravity, which don't need to say what it is in detail, but a mathematical description of the force between two masses, any two masses at any distance apart, and also laws of nature that mathematically describe motion. It worked. I don't need to go into the details for the point of view of this talk. It worked supremely well. You'll know his great and justly celebrated perception that the force that pulls a piece of chalk or an apple to the ground here on Earth is exactly the same force as the force that holds the moon in the Earth's orbit. They all are a result of this law that is pervasive everywhere and maybe throughout all time. Very important to notice, nonetheless, that although this was an absolutely astonishing achievement to have achieved that intellectual framework, first of all, he didn't do it on his own. He was standing, as he said, on the shoulder of giants, Galileo, your Keplers, right the way back to the ancient Greeks, whom he revered more than anybody else. But Newton, I think it's fair to say, was a great synthesizer as well as a great original thinker. Now, it's the fate of anyone in the field of science that their work is never finished. And Newton, for all the tremendous success that his work had, he didn't completely finish that work. There were still things he couldn't quite account for within the scope of his theoretical structure. And it's very important to notice that particularly on the continent, people were very unhappy with his conception of gravity because he didn't give a mechanical origin for it. What causes it? He didn't say. He said he didn't know what it was. He didn't feel it was necessary to specify it. So on the continent, particularly in France, Newton was regarded as a great mathematician, true enough, but as a thinker about nature, extremely eccentric. And he finished his life, poor man, tortured by gout and not in the best state, but certainly revered in Britain as the greatest natural philosopher the world had ever seen. But he knew his work was unfinished. He could not complete his calculations on the stability of the universe, aspects of planetary motion and what have you. This is not in any way to diminish his achievement, but just to say science is something that really doesn't have you don't go into science if you think you're going to solve everything you set out to achieve. What he certainly had done was to demonstrate, in the words of his great rival Leibniz, that mathematics was a torch that you could shine onto nature. It was something that the abstract complex of ideas could be used to actually shed light on the world around us. But it was something that was beyond the great Newton's ken, for example, to give a description of electricity and indeed of magnetism. That's one of many examples. That needed to be sorted out, and he was unable to do that with the tools at his command. The Newtonian project was more or less completed, not in Britain, but on the continent, in particular in France, and this is my candidate for the most important person in that completion, Pierre-Simon Laplace, known as the French Newton, especially in France. And this gentleman was a superb mathematician, a devotee of Newton, someone who was not part of the naysayers that thought Newton was not a deep thinker about the natural world, merely a mathematician. And he, with the person who was his, what we would now say, supervisor, Jean-Laurent d'Alembert, and other continental mathematicians, Clairaut, Bernoulli, Lagrange, and others, they collectively developed the schema that Newton developed, a whole new bunch of mathematical techniques that develop what we would now call the classical account of mechanics and cosmology. Now, one of Laplace's achievements, and there were many, he's not nearly well enough known in our country, in my opinion, was to write up in a multi-volume masterpiece called Celestial Mechanics, the mathematical completion of Newton's account of the cosmos, deployed with enormous mathematical power that Laplace had. One of those volumes was dedicated to his great friend and sponsor, so to speak, Napoleon, who was a tremendously beneficial force for French science, in particular the study of electricity. Now, such was the activity in France that a take-home message, it's a bit rough and ready, but it will do. It's sometimes said by historians that physics, as we now know it, broadly speaking, is pretty much a French invention that took place in the early 19th century. Now, what do we mean by that? We mean by what we now regard as something that physicists do, the topics that they study, they started to come into a sharp focus in and around the orbit of Laplace at the turn of the 19th century. The thing started to take shape. Before, other topics were allied to it, even psychology and things like that. But the topic that we now talk about as physics, that started to take shape in France in the early 19th century. And the first school of mathematical physics was run by this gentleman here in his mansion in Arcueil, which doesn't exist anymore, I'm afraid, in south of Paris. And he had around him, he held court with various students and other acolytes, guiding their development of what we would regard as a Newtonian program. But it was a more advanced program mathematically and in its range. People like Biot, Ampère, and others were there. Now, Laplace, very important to remember, totally revered Newton, but he moved things ahead. He developed the science that Newton had. For one thing, particularly important, is this gentleman here was godless. You may know the story about Napoleon asking Laplace why God has no place in these books, and he said, I have no need of that hypothesis. So he was not a natural philosopher in the mold of Newton. And he believed that in a deterministic universe where the present, if you knew everything about the present, you could predict the future and then you'd go back to the past. He was a chilly rationalist who believed, he had great faith in the existence of natural laws that could describe the universe. So we have shaping here quite a modern view of science. You go to his book, The System of the World, and you see that he's talking about phenomena all over the map in physics and believing that you can talk about interactions between particles, a more basic view of physics from which you could derive the results of experiments. Again, that Newtonian insistence that you have to use your theories, if you can call it that, and make predictions about the natural world that will be tested against nature. So this man here was enormously influential, set up, as I said, a standard way of doing physics at his country mansion. But by the time of the Battle of Waterloo, in 1815, his trajectory fell, but nonetheless, the French science continued to flourish, although with different emphases, and his rather authoritarian way of running physics fell by the wayside. One of the things that he and his way of doing, looking at the natural world, couldn't do was to describe electricity and magnetism. The person who we now know most effectively shone the torch of mathematics onto that subject was this gentleman here, James Clerk Maxwell, whom I mentioned at the beginning. Now, he was my favourite Scot ever, wonderful, wonderful person, very lovable human being, a Cambridge-trained mathematician, and a natural philosopher to his fingertips. In the mid-19th century, when he was being educated in natural philosophy and in mathematics, by then physics really had taken shape, and there were people studying optics, material structures, heat engines, gases, the sort of things that we now study in school and in early years of college. And everybody knew that what you aspired to were mathematical laws that could describe these various parts of nature. What he decided to do, and he wrote to one of his, to a very famous thinker at the time, William Thomson, that he was going, straight after he got his undergraduate degree at Cambridge, he was going to attack electricity. That's the word he used in his letter. Now, this showed the extent of his ambition, because many of the best thinkers about the natural world were working on exactly that topic, particularly on the continent. So what Maxwell decided to do was to study the relationship between electricity, magnetism, and the ether. He just saw those as a package, right? No, ether wasn't something he thought was some kind of excrescence. It was central to his thinking. The really brilliant, or one of the really brilliant things that he did was he didn't start thinking about it until he really had become acquainted with the best experimental work on that subject, which was done by his hero, Michael Faraday, a self-taught natural philosopher working in the basement of the Royal Institution, who'd done some incredibly clever and thoughtful experiments there, in addition to all the other things he did. One of the greatest scientists ever produced on, I shouldn't say scientists, natural philosophers on these shores. And it was Faraday, who was absolutely not a mathematician. It's sometimes said that the most advanced mathematics Faraday ever did was balancing the books of the Royal Institution. He was not a mathematician, but he came up with the absolutely central idea, right, which was one that we all learned about more or less at junior school. The idea of a magnet, for example, sitting there, and it has a magnetic field around it, a field that the space around it is not completely empty, but is in some sense active. It can be acted upon by that magnet. And from that, again, it's in the English language now, gravitational field, electric field. That idea was born in a modern sense in the mind of Michael Faraday, and the much more mathematically sophisticated Maxwell picked up on that, studied it, and in the course of several years, among other things, he was a very, very versatile thinker. He, in the early 1850s, came up with this theory of the interaction between electricity, magnetism, and the ether, and came up as a quite glorious prediction that out of the equations that and principles that he used to that theory, that he predicted that light was an electromagnetic disturbance, something that was only later verified. Something that I want to stress, very important about Maxwell, is not only did he have a completely peerless feel for the way nature works. It's very difficult to say what that means, incidentally, but there are some thinkers who just have this feel, they have this, it's very difficult to describe. They somehow have a feel for the way nature is built, and Maxwell really did have that. But he also was a very good mathematician, a bit scrappy, yes, not particularly rigorous, yes, but he was very interested in ideas right at the forefront of mathematics. The theory of knots, when you tie knots in your shoelaces, that's the very primitive version of the thing that mathematicians now study in a very rarefied way called knot theory. The branch of geometry called projective geometry, and a mathematical objects called quaternions. These were frontiers of mathematics in Maxwell's time, and he was fascinated by them because he thought that those mathematical ideas could be used to shine a torch onto nature. And in his great treatise on electromagnetism in 1873, you'll see references to that modern mathematics in there. He had become a very, very mathematical thinker. Not always popular. His friend and admirer, William Thomson, was distasteful of this Maxwellian inclination to mathematics. Thomson described mathematics as the etherealization of common sense and was very insistent that mathematics should be the servant of physics, not its guide. So Maxwell stood out and was, I say again, a thinker of considerable depth on this relationship between physics and mathematics. He died in 1879, far too young. I think he was 48 years old, not knowing whether that theory of electromagnetism was the right one. There were other competitors on the continent, but his field theory of electromagnetism held out and is now seen, in my opinion, quite right, as the crowning glory of 19th century physics. Now, by the time Maxwell was on his deathbed in Cambridge in 1879, there had flourished, among all the specializations in science, a branch of science called theoretical physics, particularly in Germany, where you had for the first time people who actually paid to do, not to get their hands dirty on doing experiments, but actually to think using mathematics about the natural world and to try to develop our understanding of the most basic laws of nature. It started very small, but this was the discipline whose most famous representative was to be born a generation later. This gentleman is the person I'm talking about, Albert Einstein. Einstein always described himself as a theoretical physicist, but as I shall argue, in my opinion, he was about 50% a natural philosopher as well, which I do not mean in pejorative terms at all. He was most definitely a philosophical thinker about the natural world, as well as a peerless theoretical physicist. Contrary to popular myth, he was a bright child, inquisitive, all right, may not have been an outstanding genius when he was a young boy, but he was certainly very, very bright. He was headstrong, very independent-minded, and intensely curious. By the time he went to college, he was absorbed very much in Maxwell's theory, which he said had the most impact on him. That's a very important point. He saw this. He had what you might call taste as a physicist, even as a young student, and was skipping lectures, most particularly on mathematics. He really thought, and this is clearly on the record from people that spoke to him at the time, that physics was essentially a subject that you needed only very basic mathematics to do. You don't need to go into the pure maths department and study fancy structures that the real professionals are doing. So when Einstein had his great year, his annus mirabilis, that is justly celebrated, if you look at those papers about the nature of light, on a modification of Newton's ideas on space and time, which was the special theory of relativity and his theory of Brownian motion. You look at those simply wonderful papers, and you will see that the mathematics that Einstein uses, all right, it may be beyond most of us, but it was certainly not especially advanced by the standards of a professional mathematician. And I would just make the point that Laplace, if he were looking down from heaven or wherever, right, would have had absolutely no problem understanding that mathematics. So Einstein was someone who I think it's fair to say disdained advanced mathematics. All this changed, and it changed quite quickly at around the time this picture was taken in 1912. By then, he was thinking deeply, and I don't think he thought in any other way. He was thinking about gravity and the need to, as he saw it, to set out a new understanding of Newton's theory of gravity, which could not account for a very small number of observations, for example, on the motion of Mercury. He believed on theoretical grounds that that theory of Newton's had to be superseded, and he came up with a new principle, the principle of equivalence, on which he based his thinking, but he found it extremely difficult to realize that in mathematical terms, using his assumption that everything would be simple and straightforward. It was only when he spoke to close friends, mathematician friends in Switzerland in 1912, that he started to see that the clue to solving his problem of actually setting out that theory was to use something called differential geometry, which almost certainly he'd skipped as an undergraduate. And he then saw it was experience that never left him. He saw that in that advanced mathematics was the key to solving his problem of finding a successor to Newton's law of gravity. This was extraordinary. Let me just come up with an analogy. Whenever a physicist or anybody else goes into a new field, right, they do not really know where they're going. They have a sense vaguely what they're trying to do, and they don't know how to solve the problem. This is a tough field to be in. This is like heading out into the desert, right? Not knowing how you're going to make it to the next oasis. And then finding on the side the perfect survival kit, just engineered for you. That's what differential geometry did for him. It was sitting there waiting for him and was perfectly suited for the development of his new theory of gravity. He delivered that theory in November 1915, having nearly been given the biggest shock of his life. Why? Because he found it an enormous struggle to complete that theory. Right? Not just the mathematics, but the interpretation. It was an extremely difficult problem, and he found it very, very difficult to finish off. He actually came very close to the answer about the time we took this picture, but he couldn't finish it off. And he very bravely, I think, went down to Göttingen and spoke to the mathematicians there about his incomplete theory. And the great mathematician David Hilbert, who was then past his best as a mathematician, saw that this Einstein was a tyro in mathematics and was right on his tail, breathing hot breath down Einstein's neck. He was literally days behind him. And Einstein did finally beat Hilbert to the goal and set out that new law of gravity in November 1915. Now, what is important here is that Einstein, by his recollection, got to that goal guided by mathematics. That when he found the right natural structure, then the problems he'd been wrestling with fell away. And this became the most important guide to him about the way to do theoretical physics. You trust mathematics to deliver it for you. Very important to say that excellent scholars, Jürgen Wren and his colleagues, have looked at Einstein's notes on this and shown that that is a very partial way of looking at that research. In fact, he was looking at both what we call a two-pronged strategy, looking at the experimental side, the need to be consistent with Newton's law and what have you, and the mathematics alternately, right? Whereas Einstein had a very partial recollection of this, that it was the mathematics that delivered. Now, Einstein was the only person there, I guess, right? But this became his credo, right? That mathematics would lead you to develop your theories. Having had this colossal success of producing a brand new theory of gravity, and let's face it, you have Newton's gravity that explained almost everything, and you produce a successor that reproduced everything Newton did and had made additional predictions. Einstein wanted to go one step further. He wanted to take that theory of gravity and extend it so that it included electricity and magnetism. Now, how do you do that? What most people would do is look for experimental clues. That's the orthodox way of doing it. Ask experiment to give you a guide. Now, Einstein's view, taking that philosophy that I just spoke to you about, was not to do that, because there weren't any clues, but instead to generalize the mathematics of his theory, to focus on the mathematics. This was seen as a very eccentric way of proceeding, let's be clear. There were very few people that took this seriously, and he was ridiculed by his frenemy Wolfgang Pauli for, as Pauli put it, moving over to pure mathematics, of playing with what Pauli called a completely squeezed out lemon, which was the general theory of relativity. It was seen as a completely foolhardy activity. And he didn't actually really go public with his philosophy, of this mathematical philosophy, for some years. He finally did so in Oxford, at Rhodes House. A nice building now. I think it's a very good wedding venue, but theoretical physicists, especially ones that know about Einstein, think of this as where Einstein actually went public with his philosophy, his way of doing theoretical physics. And this was in 1933, Saturday, the 10th of June, just after or around exam time. This was a societal highlight of the season. Einstein about to flee to the United States of America, his life having been made impossible by the rise of the Nazis. He was staying in Christchurch, and this was to be the first lecture that Einstein gave purely in English. And he was seeking accessibility. He knew that there'd be people in that audience who didn't know anything about relativity or atoms or anything like that, so he wanted to speak in plain English. And he gave a talk there that a title, even the title is significant, The Method of Theoretical Physics. Notice, not a method, not my method, the method. And it was a method almost nobody else was using. This is fake news. This is a mocked up picture of Einstein in Rhodes House, right? Pretty much what those people would have seen when Einstein was giving that lecture. Thanks to my friends at Rhodes House for allowing me to take that picture. He presented in a very friendly way to his audience. I don't think there's a single mathematical symbol in the lecture, about his project of generalizing his theory of gravity so that it included electricity and magnetism. And as I said, not focusing on experimental clues, but focusing on mathematical structure. He said in the crucial line of that lecture, and I've had it multiply translated by German scholars, right, and they all say the same thing, right, that the creative principle of the theory is in the mathematics. He was that strong. He believed that's where the creativity lied. I say again, very, very controversial and singular way of looking at developing theories. The embarrassing thing was, and I'd be very respectful when I say this had got him nowhere. He was making very little progress on this subject. One of the reasons why was because the new discovery of quantum mechanics, which was the theory of motion on the atomic scale, showed that nature was granular and had these discontinuities at small distances that Einstein's thinking could not encompass. So Einstein was not going to be deflected. He was an extremely stubborn person. I'm sure he'd be very proud to hear him described like that, because that's what he was. But he knew that the new generation was coming up, and that the new kids on the block who were taking over from him as the preeminent physicists of the time, and these people were almost all the young quantum theorists. This is a famous picture of the Solvay conference in 1927, where many of the pioneers of quantum mechanics are sitting round the person who knew his place in the physicists in the community, Einstein, sitting front and center. And there are many of the pioneers of this most revolutionary theory of the 20th century, much more revolutionary than the general theory of relativity. Why? Well, Einstein always said that the general theory of relativity was meant to be a generalization of the Newton theory. He did not see it as revolutionary. He said that more than once. Quantum theory was seen to be a sharp break with the theory that went before it in order to understand this bizarre behavior of matter on the atomic scale. Now, the one I want to concentrate on is the person who was quite proud to have his picture taken here. And this gentleman's name is Paul Dirac. And you can see him there sitting on Einstein's right shoulder. Now, Dirac was a very modest person, right? But he was not too proud to send a copy of that picture to his school. He was very proud of sitting right behind his hero, someone who turned him onto theoretical physics when he was a teenager. Now, Dirac did not invent quantum mechanics on his own by any means. It was two other people, Heisenberg and Schrödinger, who got the ball rolling. Dirac then moved in and became one of the pioneers of the subject. But what distinguished Dirac was his particularly mathematical approach to the subject, and that's why he interests us in this lecture particularly. Dirac had come as an outsider into theoretical physics. He'd done an undergraduate degree in engineering, learning how to fill in tax forms, learning about aircraft, motor cars, and what have you. He then did a degree in mathematics, both in Bristol, and then he went to do a PhD in Cambridge, right, having had no formal training in theoretical physics. When he read Heisenberg's paper, he was brought into that field and then shot to the front line and became a peer of those people. Dirac had this knack of taking projects in quantum mechanics, the study of this motion at the atomic level, and finding and linking it to modern mathematics. I might say not doing it on purpose, but he found himself doing modern mathematics. Give you an example of that. When he read that first Heisenberg paper in his parents' house in Bristol, he saw something, just a line that you can go home and read tonight, whereby in Heisenberg's way of looking at motion, you take two objects, A and B, and when you multiply them together, the order of multiplication matters. Everyone here knows that 6 times 9 is the same as 9 times 6, that 10 times 4 is the same as 4 times 10. In quantum mechanics, you take these two operators and the order actually matters. Now, the horrible word that Dirac unfortunately coined for this was non-commutation. It means the order of multiplication matters. Heisenberg, by his own admission, said, well, this is probably, this looks a bit embarrassing, we'll sort this out. Dirac saw that as key. Non-commutation is a key theme of 20th century mathematics and was absolutely central to the way that Dirac developed his version of that subject. What Dirac is most famous for is coming up with an equation for the first fundamental particle to be discovered, the electron, and combining special relativity and quantum mechanics into a description of the electron. And it brought him into the mathematics of spinors that describe the behavior of the electron. Spinors were discovered a few decades before in Germany, describing the motion of a spinning top, and Dirac had hit on that and hit on spinor geometry, which is a very important theme in 20th century mathematics. And in his, for my money, it's only a personal thing, his greatest paper, which is on how quantum theory leads naturally to a theory of a magnetic monopole. Everyone knows that magnets come in north and south, but in quantum mechanics, it's quite natural to have a monopole, a north alone, a south alone. And in doing that, he was driven to be doing creative research in the field of topology, which is about the properties of shaped things that don't change when they're stretched or but not torn, but otherwise distorted. So Dirac, those are the three good examples. There are others. He kept finding that physics took him to mathematics, and that mathematics then guided him in his approach to physics. He, in a wonderful phrase that he coined in 1975, and it's a very resonant one, is that mathematics will lead you by the hand and take you to new paths and new territory where you can take stock. Now that's a critical phrase, ladies and gentlemen, right? He's saying that if you trust in mathematics, it will take you to places that will enable you to make progress. Now, one thing that even his worst enemy wouldn't say about Dirac, right? No one would ever call him a philosopher. He was an anti-philosopher. So he must have been quite surprised at the end of 1938, this is what, 12 years after this picture was taken, to be invited in Edinburgh to give a talk on the philosophy of physics. This is something that Dirac had no interest at all in, but he decided to take up the topic and gave a talk on the relationship between mathematics and physics, which was a topic, remember, that Maxwell spoke about in 1870, do you remember? This is one of the great lectures of Dirac's oeuvre, and indeed one of the great lectures, in my opinion, public lectures in theoretical physics. You can go and read it online. Anyone can read it. It contains no mathematical symbols at all, so far as I can recall. This is more fake news. This is another mock-up of Dirac standing outside the Royal Society of Edinburgh, in central Edinburgh, and this is what it might have looked like on the 6th of February 1939. Storm clouds gathering very close to the beginning of World War II, and Dirac gave a lecture that lasted an hour, and he reviewed right from the most basic level. The cleaner in that organization could have listened to the opening of that lecture, right? He talked about how the universe or the world around us has a mathematical quality that is not obvious to people until they begin to study it in detail, right at that level. And then he goes right up to the application of quantum theory and relativity, using no mathematics, but thinking about how we could develop, or how he and his peers could develop their thinking about the subject. It's most famous among people today, being the place where he coined his principle of mathematical beauty, which is the statement of extremely bold, some people would say overly bold and perhaps even foolish statement, right, that physics advances, fundamental physics advances from one theory to the next through increasing mathematical beauty. You start off with something that is relatively ugly, and the theories gradually become more mathematically beautiful. Now, even if you're not a professionally trained philosopher, you don't need to see there's a big hole in this argument, right? At least, I mean, without being disrespectful to Dirac. How do you define what beauty is? People have different views on this. Dirac had no time for that at all. As far as he was concerned, in mathematics, you really do know what beauty is, and he stuck by his guns. And it was, as he said in later life, almost a religion. He believed that mathematics, beautiful mathematics, would take you to correctly to the next stage. Now, these are three statements that I just want you to look at, and they're statements where I wish people of Dirac's stature could all write like this, with, in my opinion, truths of great beauty themselves that are very, very simple. Look at that. Look at this for a statement. The mathematician plays a game in which he himself, sorry about the sexism, invents the rules, while the physicist plays the game in which the rules are provided by nature. That's it in a nutshell. That's why physics and mathematics are different. They are not the same thing. Very important to realize that. This is even more germane, in my opinion. The rules that the mathematician finds interesting are the same as those that nature has chosen. Now, that's not obvious. Why should it be, right, that pure mathematicians looking at these patterns of ideas are finding themselves on the same territory that state-of-the-art theoretical physicists are working on as well? That is not at all obvious. And this is almost wild, this lecture at certain points. I mean, for Dirac, a very reserved, very quiet-spoken person, wild in the sense of he really does talk in a very bold sense about the future of the subject. Makes one observation which I love, which he was saying that philosophically the most interesting thing about theoretical physics was not quantum theory of relativity, it was cosmology. Now, I wasn't expecting to see that. Now, today that looks extremely modern. Right? That's what he says in passing in this lecture. It's an amazing lecture. And he also says, possibly mathematics and physics will one day unify. Now, that's also a very bold statement, but one that is coming back into fashion. It may not be correct, but it's something that's starting to look very modern, as we'll talk about. Now, that unity certainly didn't come after the Second World War. As Freeman Dyson has explained in his many talks with me at the Institute for Advanced Study, Freeman began life as I think it's fair to say, a mathematical prodigy, a number theorist trained at the feet of G.H. Hardy at Cambridge University. And by Freeman's account, although he was a totally gifted mathematician, he found that the mathematics he was doing at Cambridge was not the stuff that was really cutting edge at the time he was there, which is in the Second World War and shortly afterwards. The pace setters were known as Bourbaki, which is an organization of French mathematicians, anonymously grouped up under that name of Bourbaki, who first met in 1934, with the ambition to rewrite the whole of mathematics set out as axioms, to make plain the unity and logical structure of mathematics. The one thing it wasn't interested in was applications to the real world. Had no interest in them at all. Freeman told me that he heard the Bourbaki agenda at Cambridge referred to as a French disease. Now, I didn't know that was a synonym for syphilis, but it is. They certainly had no time for Bourbaki at all. Freeman chose to concentrate on problem solving. And that's what led him to his triumph in setting out a quantum theory of electricity and light. But his observation that he's rammed home to me many times is that at that time, after the war, there was a divorce between physics and mathematics, where the two went their own separate ways. Something that was confirmed by a Princeton colleague, Karen Uhlenbeck, winner of the Abel Prize this year, who had exactly the same experience, or very similar experience 20 years later, where the gradual coming together of physics and mathematics was viewed as something to be as deeply suspicious. Now, I'm afraid I'm having to go through far too quickly the second part of my talk here, but so you'll forgive me if I go quite a gallop here. Where I come in as a spear carrier was in this era, 1970. Right? And this is when I became a student. Now, this, of course, is the sexier side of that time. In fact, it was pretty a miserable time. As I remember, these wars in Southeast Asia and the Middle East, UK economy plummeting, known then as the sick man of Europe. Nothing much changed there then. But for me, and for far more eminent people than I could ever aspire to be, this was a time of huge excitement. And the reason for that was because of the activity in understanding the subatomic world, the subject of particle physics, and also on the macroscopic scale, astrophysics. And I must admit that, not being particularly mathematically inclined myself, I was very suspicious to see these incursions of mathematics made at that time, when it seemed to me that the real action was in accounting for experiments. Now, with the benefit of hindsight, the critical thing that was starting to take shape then, and I urge this as the take-home message tonight because it's still true today, is that the theories that if you want to produce a fundamental theory, then as Dirac had alluded to in that lecture, those theories must be consistent with the special theory of relativity, theory of motion, that Einstein and others had put out in 1905, and quantum mechanics. Nobody has ever done an experiment that has contradicted those two theories. So it's an incredibly strong empirical base. And what physicists have done, much of what they have done in basic physics, has been jamming those two theories together. Now it really is worth stressing that is extremely difficult to do. Einstein thought, and he was not alone, thought that it was impossible to take theories that look so different with such different mathematics and find a way of jamming them together such that they produce just about a theory that works. And it did, because it produced the first theory of what we call quantum electrodynamics, which is, I believe, the best verified physical theory in nature. And it also triumphed in astrophysics as well. I remember when I was a 25-year-old graduate student going to a lecture, not here of course, but in Oxford, given by the great Dennis Sharma, when he was talking about the way Stephen Hawking had shocked his community by putting forward this idea that you could actually bring in quantum mechanics to the study of black holes, which is a classical subject, and come up with this physical notion that black holes ain't so black, but actually continually emit radiation. Something that I saw people saying it was completely nuts at the time. Now it's part of the textbooks. But he did it with a tour de force calculation that did not combine them rigorously in one fell swoop, but brilliantly brought the theories together in a way that made the calculation extremely robust. I still remember that talk, and still remember Dennis's admiration and excitement. For the people in the audience, of whom I was one, what we were seeing was a different jamming together of quantum mechanics and relativity, the gauge theories of the forces that govern the atom. Now, this theory was we now call quantum field theory, governing the basic interactions that hold together the nucleus and the atom. I say again, it's amazing that the theory even exists, right? But it does. Right? And by very careful study of the symmetries, the leading theoretical physicists found what we now call the standard model that has had nothing but ticks from nature for decades. So this is an extremely powerful way of doing theoretical physics. I want to illustrate one particular meeting that really brought, in my opinion, and it's central to my book here, that was the central moment, I think, when, or a central moment, when mathematics and physics really did start to come together and the divorce became a thing of the past. It was the meeting between the great mathematician for many years here at Oxford, Michael Atiyah, and below Edward Witten, the American mathematician. Atiyah was a great geometer, without question one of the great mathematicians of the 20th century, and he had become interested in these gauge theories that govern atomic physics, as I described. And in the early 1970s, as he described to me, he began to morph into a quasi-physicist. And the person who he was most close to was Edward Witten, many years his junior, a complete singularity, an outsider like Dirac, an undergraduate in modern languages and history, and briefly studied economics. And by the time he switched, I think it was the age 23, he switched into theoretical physics. And they met in the fall of 1976 in an office in the Massachusetts Institute of Technology. Michael Atiyah has described that meeting to me a dozen times. He was there was about 12 people sitting around a small office in there, and he said one person knew more than everybody else put together, and that was the recently graduated PhD, Edward Witten. Together, they Edward had begun work just by, but not just, I shouldn't use that word, looking at data closely, working out what one could derive from it, but with encouraged by Atiyah and with an enormous mathematical ability of his own, they started to bring those two subjects together and analysed ever more closely the mathematical structures of those gauge theories. I can't resist, in a tribute to Michael, who died a few months ago, his favourite image, that it was like having two intersecting tunnels, one being dug by gauge theories, the other being dug by mathematicians. They were oblivious of what each other were doing, and at a certain point they intersected and found they were working on each other's subjects. That intersection, ladies and gentlemen, took place at the Mathematical Institute of the University of Oxford. That is when I would say those two things intersected, and Frank Yang, who also has a claim for being part of this, that is where it took place. And in 1977, Witten, Atiyah, and several other very eminent scientists were working on that common territory between pure mathematics and theoretical physics, studying monopoles, things called instantons, which are events in space and time, and beginning to apply it to other subjects as well. Latterly, we now know the physics of solids. I saw, to my dismay, I have to say, because I wasn't anything like as sophisticated mathematically as one needed to be, I thought this would go away. I thought that nature couldn't be that complicated, right? But it has stayed. The subject's mathematical complexion has endured. And particularly through the next generalization of quantum mechanics and relativity coming together in something called string theory, which, as Witten has said, wisely in my view, is the only interesting idea that is a development of both general relativity and the gauge theories of atoms. String theory began to take shape properly in the summer of 1984, when we had a viable account of not just gravity, but the three fundamental forces that hold together atoms. And for the first time ever, it gave a reason why gravity must exist. Witten said to me that is the main reason why he was interested in string theory. And it became, this is a key point for us, this became a Klondike for mathematicians. Even today as we speak, I think it's fair to say that that string theory has above all been of enormous benefit to mathematicians. And there have been other developments of two by physicists, something called M theory, which is a generalization, a further development of string theory, and 2 years later, one Maldesena's linking between string theory and gauge theory. It appears to people working in this field that these mathematical connections demonstrate that physics is on the right track. It would be idle to pretend that there aren't people who oppose that view, and their calling card mainly, or the biggest one, is that string theory has yet to make a direct connection with experiment by virtue of a new prediction that can be tested in laboratory. That cannot be denied. That hasn't happened. But string theory lives, if that's the right, which most naturally applies at very, very high energies. So it's going to be very difficult to test, which is not to say it's impossible. But nobody has actually contradicted it, but there are, without doubt, there's reasons to be concerned about the interpretation of it. And I might say as well, its connection with ordinary space-time, the one that we live in, is also problematic. That cannot be denied. But what I would like to say is that the application of string theory is such that people who are the best experts see that still as the most promising theory. There are people who disagree with that. It's a free country. They can work on those other topics. But I think it fair and reasonable to say that these other competitors are a minority sport. They may disagree. Of course, they're free to do that. So let me just look, if I may, to what we now call the doubly unreasonable effectiveness. Mathematics, of course, is incredibly effective in physics, but physics now, we know, more than ever, is extremely effective in mathematics. And I've given several examples of here, which are and I'm not going, because of time, I'm not going to go through them, forgive me, but I cover them in detail in my book. There is absolutely no doubt that physics and mathematics are joined at the hip in fundamental physics today. So what's my view of looking to the future? Well, my view is that there is good reason to believe that we are on the right track, guided by quantum mechanics and special relativity, but that we definitely need to be patient. My generation, if I can call it that, was used to results coming every few years, major new results that were rich pickings from Mother Nature. Today they come much more slowly. And I think we're going to have to, in physics, we're going to have to get used to the mathematical timescale where things are done much more slowly. These are my predictions, all silly, right? Well, at least they're not intended to be silly, but they probably will be. But I want to show why I think this is, how I think this, what we're aspiring to here. First of all, I predict that the quantum field theories that are now used to describe atoms, which are extremely difficult to calculate, that is ripe for a completely new understanding. Quantum field theory will be reformulated in a way where these horrendous calculations will be much simplified. There are already evidence to get us started on that. I predict that will happen. I also predict that string theory, yes, I'm sure there are things that need to be radically revised in the theory. I'm sure there may be even revolutions around the corner, but I believe that this is not wasted effort, that this will be seen as a perfectly worthy step on the path to the future. The understanding Maldacena gave us of gravity in terms of an equivalence between a string theory and gauge theory, I believe will be seen to be applicable to the real world. Most important, this is a particularly big thing that I can't explain in detail, but I talk about in my book and you can read elsewhere. Space-time, developed most famously by Einstein, that is going to be superseded. I don't know of any leading theoretical physicist now who believes that the Einsteinian view of space-time is complete. It is going to be superseded, and we're being guided on that track, I say again, by quantum mechanics and special relativity. And we're seeing, I think this is very heartening, a trend towards unity. Particle physics, cosmology, condensed matter, that's solids, information theory. There is a coming together of areas all across fundamental physics, with mathematics being the glue between them, and mathematics providing a guide to help us understand those relationships. So I think we're going to have to get used to something, that surprising new insights from experiments and observations will start to become few and far between. Right? I know it's a bit depressing, but they're not going to come every few years. Nature is getting harder and harder to question constructively about these things. So I think physics, as I said, is going to be a longer term thing than it seemed when I was starting out. During those slow decades, and I think we're in one now, physicists will have to focus, I think, on mathematics. And do, as Einstein said, and Dirac said, and others have said, but those two, I think, were the pioneers, that by looking at the mathematical content, you will be able to advance the subject so that it's ready for the next generation of experimenters. Now, it seems a harsh thing to say, but I believe we're going to have to take this, while it's difficult to get clues out of nature, we can console ourselves that nature doesn't speak to us just in terms of observations. It also speaks to us in numbers. Thank you very much.